Okay, on to our final question, and this is the buffer overflow question. So keep in mind when you're taking the exam, if you're doing the buffer overflow question, something should get overwritten probably. So things should go wrong. Generally, you should see something weird happening, right? Because this is something that C allows that's not sort of normal, right? It's a logic error that comes into the program or that an attacker forces into the program. So you should see weird things happen, right? So you're a hacker, you're using the debugger to discover the information above for a user-defined function of a program through fuzz testing and analysis. You discover that a string can be placed into memory through a user input, and that the input is stored starting at address BFFF7DO. So we're given this information about EIP and ESP and EBP, and so we know a little bit about our stack, right? We know that EBP is at OX BFFFF7F8. We know that that's our sort of garbage value for the stack. This is a user-defined function, and so we actually also know that there's some buffer here, and we're given that that buffer starts at byte OX BFFFF7D0, right? So that's given in the problem statement here. So we're taking EBP from our debugger output, we're taking input from there, and that sort of tells us like how much space we have to put something into memory, or to put this attack into memory. We also know that below this is prior EBP for 4 bytes, and then we have the return address for 4 bytes, right? So that's what we know from the prior problem. We have this nice diagram that shows us what a user function looks like. So we have our user function variables, of which buffer is one of. We have prior EBP and the return address, right? And then the stuff that we got from main. So we kind of know that that's what our memory looks like, and that's going to be necessary for part A here. So for part A, what is the minimum number of characters that the user will input to overwrite the first byte of prior EBP? So we want to know if we put something into buffer, how much stuff do we have to put in there that this byte that we would consider garbage gets overwritten, right? And that might mess up our memory, might cause the program to crash. So this is something you would figure out during fuzz testing. You'd enter a bunch of different letters of different lengths, and then you would find which one causes the program to start to fail. So how many do we need? Well, we're trying to get to here. We're starting here, so we need to do the math and subtract OXBFFF7F8 minus OXBFFF7D0. So this is our first byte of prior EBP, and this is our first byte of the buffer, right? So that's the string that we were able to input. So let's do the math. All these are going to cancel out. Our 7s are going to cancel out. So OX 0, 0, 0, 0, 0, 0. 8 minus 0 is 8. F minus D is 15 minus 13. So that's going to give us 2. So we have OX28. And we want to know number of characters, which we want to know that in decimal, not hex. So we're going to convert OX28 to decimal, which is 2 times 16 is 32, plus 8 is 40 bytes slash chars is what we're going to enter. And keep in mind, there's a null at the end of that, so that null is actually what ends up overwriting, right? We're going to fill this with 40 bytes, and then the null overwrites the first byte of prior EBP. So then your shellcode exploit is 20 bytes long, and you repeat a malicious return address 3 times. What's your minimum NOP sled size that you need to perform the buffer overflow attack? So that buffer, what we want to fill it with is NOPs, and then shellcode, and then repeated return address, repeated malicious return addresses, right? So that's what our buffer overflow exploit looks like. So it says that this bottom part is repeated malicious return address 3 times. So 3 times 4 bytes for each address is 12 bytes of malicious return address, right? So that's how much space we're taking up for that, plus 20 bytes of shellcode, right? That's our exploit. And that gives us 32 bytes total that we have for the buffer overflow attack, right? And so we're almost there. We know that within the buffer, then we have 8 bytes of space left, but we need to remember that what has to happen is this malicious return address has to overwrite the return address itself, right? And so we need to not only overwrite the full 40 bytes of the buffer, but we need to write into the malicious return address so that the return address itself, so that one of those malicious return addresses overwrites our actual return address, right? So that means we need the 32 bytes there plus the 8 bytes that we have left here. So 8 bytes in buffer plus 8 more bytes to overwrite return address, and that gives us 16 bytes of no ops. Okay, and so then on to part C. Using your answer for part B, will your attack succeed with a repeated malicious return address of OXBFFF7CF? So we need to know, where does that fall in our buffer? And if we look at where CF is, so 7CF is going to be below ESP, but it's actually going to be, OXBFFF7CF is higher than D0. So this is earlier on our stack than our NOP sled, right? Which means that we don't actually know what's there. It might be other data, but when we interpret that other data as like instructions, it's very likely it's just going to crash the program. So no, because OXBFFF7CF is not inside the NOP sled or inside the vulnerable buffer. Right? So we just don't actually hit our target here. Part D, using your answer from part B, will your attack succeed with the malicious return address of OXBFFF7D8? So let's look at what that is. We've got 7D0 is here. So we're in the buffer now. We're in close to the correct space. So the question is, if we hit here-ish in 7D8, is that within the NOP sled? We said we have 16 bytes of no ops. And so 7D8 minus 7D0 is just going to be 7D0, 8 bytes. 8 is less than or equal to 16. And so that means, so we land in the NOP sled and the attack works. Right? As long as we land either in the NOP sled or just on the shellcode itself, the attack is going to run, and it's going to run to completion. So because we're within the NOP sled, we just kind of slide down to the shellcode and then we execute the attack. And then part F, so this is name and describe one technical defense method that could be used to protect against buffer overflow attack. So the answers you should give here are ASLR, address space layout randomization, randomizes addresses in text segment / stack. So it just makes it harder for an attacker to figure out what's going on. A stack canary notices when the stack is overwritten. Or the final one is the non-executable stack. Cannot execute code on stack. So when we insert this this exploit, so cannot execute exploits on stack. When we insert this exploit code, this shell code on the stack, it's not able to execute. And I'm here to tell you these are like 20 years outdated. There are new defenses against this, but none of them work. So we can't defend against this in reality. That's it for the exam. Good luck, everyone.